When we study physics, an important initial step is to understand physical quantities and measurement. In this video, let's explore all the physical quantities in mechanics, learn how they are connected to each other, and determine how to calculate each from position and mass. This video will help you to build a strong foundation in physics. So watch till the end and pause to look at the math. In our quest to build a better world and understand the workings of nature, measurement plays a pivotal role. These measurements serve as the foundation for scientific investigation, allowing us to unravel the intricacies of the world around us. If we look at any object, there are many things that we can measure about that object, such as its mass, velocity, momentum, etc. But the amazing thing about these quantities is they are connected to each other, and knowing just two quantities is enough to calculate almost all other physical quantities. Let's understand this intriguing connection by studying the motion of a car. Imagine that we are inside a moving car and we have weighed it on a weighbridge, which tells us its mass is m. Additionally, our car is equipped with a GPS device that provides complete information about its position. Using only these two quantities, mass and position, let's see how we can calculate almost any quantity about this car. Let's start with the displacement of the car. If we calculate the change in position, we have the displacement. Displacement simply means the shortest distance between 2 points. If we take the time derivative of position expressed as d by dt of x or x dot, we get the quantity called velocity, which represents how fast the object is moving. Multiplying mass by velocity gives us the quantity called momentum, which describes the amount of motion the object has. The change in momentum gives us the impulse. If we take the time derivative of momentum, we have the force acting on the object. Knowing the force and dividing it by mass gives us the acceleration of the object. This can also be found by taking the time derivative of velocity, and it represents how fast the velocity is changing with respect to time. Using the quantities of mass and velocity, we can calculate the kinetic energy of the object. By using the force and displacement of the car, we can calculate the work done on the car. Taking the derivative of work done gives us the power experienced by the car from the road due to its engine and wheels. Now let's explore the quantities related to rotational motion. Consider the wheel of the car, and by taking the car's wheel's center as our origin, let's try to explore the quantities in rotational motion. Let's assume we know the complete information of the wheel's moment of inertia, which is a quantity similar to mass in translational motion. If we also know the position of a certain point of that wheel over time, almost any quantity of that wheel can be calculated from them. If we measure the location of this point over a period of time, we can calculate how much the wheel has turned over time, which is called the angular displacement. If we take the time derivative of angular displacement, we get the angular velocity. If we take the time derivative of angular velocity, we get the angular acceleration, which represents how fast the angular velocity is changing with respect to time. By multiplying the rotational inertia and angular velocity, we have the angular momentum. Angular momentum is a measure of the rotational motion contained in an object. By taking the time derivative of the angular momentum or multiplying the rotational inertia and angular acceleration, we have the torque experienced by the car's wheel. Torque is the rotational analog of force. Now, by using the rotational inertia and angular velocity, we can calculate the rotational kinetic energy. By using the torque and angular displacement, we can calculate the rotational work done. If we calculate the rate of change of the rotational work done, we have the rotational power. Now let's go to the subatomic particles and see if this factor of determinism exists in this realm. Even for the subatomic particle, if we know two things, that is position and momentum, then we can calculate almost any other quantity of that particle. Dividing p by m, we get the speed of the particle. Using the relation ke equal to p squared by 2m, we can calculate the kinetic energy. Using lambda equal to h by p, we can calculate the de Broglie wavelength of the particle. And it goes on like finding the wave function, probability density, quantum states, etc. But there is a limit here, since it is impossible to calculate the position and momentum of a particle precisely and simultaneously according to Heisenberg's uncertainty principle. Quantum mechanics introduced the concept of probabilistic behavior at the microscopic level. According to the Heisenberg uncertainty principle, there are inherent limits to simultaneously knowing the precise values of certain pairs of physical properties, such as position and momentum, with arbitrary precision. Quantum mechanics introduces a fundamental level of uncertainty and indeterminism at the quantum scale. It really points out the limits of the observer in the universe, an enigmatic restriction imposed on the observer from preventing him from knowing too much about the universe. Great. You reached the end of this video and the beginning of our great physics course, where we will cover physics concepts for students for free. If you enjoyed it and found it useful, let us know in the comments. Share it with your friends, and don't forget to hit that subscribe button so you don't miss our next video.